Apologize for the late start. I had an issue where my entire screen didn't seem to be showing up on the stream, and hopefully that's been solved. Just want to wait a moment to see if my test message shows up. There's always about a 30-second delay, so I have to wait 30 seconds to see it on my screen when I do something here. All right. Okay. So it looks like we're good. All right. So I hope everybody has had a good week. So mine's been pretty eventful. I finished my master's course. I received an A+ in practical algorithm design. My daughter made me a new avatar for my channel and then changed the background to yellow for me. Shot a few lessons in pre-calculus, and I'm at the darkest dungeon in Darkest Dungeon. So with all that out of the way, here's what I plan to cover today. So I collected your questions before the lesson. Things that were brought up in particular were variables and how they work in relation to radicals. So I have a few examples planned for that. There were some questions on simplifying. And there were some questions on adding and subtracting. And these two kind of go hand in hand. So I've picked a few example questions with your suggestions that I plan on going over today. There were also a few questions on multiplying, and there were some lessons that were brought up there were some questions that were assigned that were introductory questions on multiplication. If you haven't watched the video yet, because it hasn't been assigned in your classroom, I have the 5.2 videos up on my YouTube channel. So you might want to give them a check before attempting any of the multiplication problems. So it's the 5.2.1 multiplication, so you can find it on the channel later on. Okay, so as I'm going through, if you have any questions, please ask them in the chat, and I will be happy to address them as I see them. Otherwise, I'm going to start off with some questions on simplifying radicals. So this was on page 279, question number 4C. So if you have a textbook nearby, you might want to grab it out. If you don't, if you have a piece of paper, that's fine too. The question was to simplify 1 over 2a times the cube root of 7a, I believe. This was 4C. Just let me check my textbook. All right. Oh, before I forget, I also wanted to talk about restrictions in more detail. After watching over my video, I think I have a few more things to say, and I might shoot a supplementary video on that as well. Okay. So let's get started. We have 1 over 2a times the cube root of 7a, and I believe the goal of this question is to convert this into an entire radical. At least I hope that's the goal of this question. I don't have it on that page right this second. So what we're going to do is we're going to take this expression, 1 over 2a, and to convert this into an entire radical, we want to move that under the radical symbol. This has an index of 3, so that means we're going to need 3 copies of that. So cube root of 7a, and we want to multiply this by 1 over 2a, and we want to put 3 copies of that factor inside the radical symbol. I'll just note as I'm doing this, by the way, I'm showing more work than I would necessarily require of you if you were doing this question, but I just want to make sure that I show everything in as much detail as possible. So the step that I probably wrote I would consider optional, but let's take a look. So 7a, multiplying the numerators together, and that's just the same thing as 7a over 1. So 7a times 1 times 1 times 1, that's 7a. In our denominator, we have 2 times 2 times 2, which is 8. And we have a times a times a, which is a cubed. Looking at this fraction, we see that there's a factor of a in the numerator and a factor of a in the denominator. We could have also reduced it back at that step if we wanted to. So we're going to reduce the two of those. And that leaves us with the cube root of 7 divided by 8a squared. And just looking at my stream, it seems like my head is cutting some of this off. Oh, I'm having that issue again where it's not all showing up. Okay, we'll work through it. We'll figure it out. So cube root of 7 over 8a squared. The restriction in this place, well, just that we have this a in the denominator of our fraction. So we know that we're not allowed to divide by 0. Dividing by 0 is undefined. So we have to make sure that we put in the restriction that a cannot be equal to 0. Now, speaking of restrictions, before I go on to the next question, I want to kind of drill down on when those restrictions are occurring, specifically looking at the index and whether it's even or whether it's odd. So, what is a radical? So both of these expressions, so the cube root of 8 is equal to 2, the square root of 4 is equal to 2. What is actually happening here? Well, what this tells us is we want to find the answer in which if we take that number and raise it to the power of 3, we will get the value that's inside the radicand. So what number, when we raise it to the power of 3, gives us 8? That number is 2. So 2 times 2 times 2. We can double check that. That's equal to 8. Correct. Oh, I see my father has showed up for this chat. Welcome, Dad. And yes, I've now fixed it. There's a problem where my stream is 30 seconds behind. Anyway, we're all good. The second one, square root of 4 is equal to 2. So what number, when I raise it to the power of 2, gives me a 4? Well, that's 2. 2 times 2 is 4. So we can see that that's the case. All right, let's just look at these. The cube root of negative 8 and the square root of negative 4. Do they have solutions? Well, for the cube root of negative 8, we would want a number such that when we raise it to the power of 3, it gives us negative 8. Does such a number exist? It does. Negative 2 times negative 2 times negative 2 is equal to negative 8. So there is actually a solution for the cube root of negative 8. How about the square root of negative 4? Well, 2 times 2 gives us a positive 4. That doesn't solve it. Negative 2 times negative 2 gives us a positive 4. That one doesn't solve it either. So in this case, there are no real solutions. There is something called imaginary solutions. That is something that you're going to cover in future classes. So that's not something that is a pre-calculus 11 topic, but you will see it next year. Okay, so there are no real solutions to the square root of a negative value, but we did find real solutions to the cube root of a negative value. So it turns out that the relationship here is when the index is odd, positive or negative radicands will give us solutions. But when the index is even, only a positive radicand will give us a solution. A negative radicand will not give us a solution. So that's why sometimes you're seeing a restriction, sometimes you're not seeing a restriction. In this particular problem, we're taking a cube root. Well, turns out that our a value is squared here regardless, but we're taking a cube root. We would not have to put the restriction that a variable would have to be greater than 0 in this case, because it's possible to have a solution when we're taking the cube root of a negative value. But if we were taking the square root of a variable, we would have to put in that restriction because we cannot take the square root of a negative. Okay, so we'll look at this in the terms of some problems shortly. I hope that clears perhaps things up a little bit. I'm adjusting my screen as I see a problem on it. Just realize that there's some lag between me writing on the screen and what you see on your screen. Okay, next up. So I had page 279 for D. So this is another simplification. In this case, it is the cube root of 128 times x to the power of 4. Just going to mess with my settings again and see if I can get this working a little bit better. I think it looks even worse now. Okay, I think I'm going to have to live with that for this stream. Okay, so the cube root of 128 times x to the power of 4. So we have 128 in our radicand. Does 128 simplify? Well, to figure out whether or not it simplifies, we're going to have to figure out what its prime factors are. So we're going to need to do a prime factorization of the number 128. Now, perhaps you might immediately recognize 128 as one of the powers of 2. Perhaps you don't immediately recognize it. If you're scrambling to find a factor, I mean, in this case, it ends in an even number. You know 2 has to be one of the factors. So even if you can't find a larger factor, which will divide it up a little more easily, you know with certainty that you can start with 2. And now that we have 2 here, 64 is 8 times 8, with one more multiplication symbol than I intended. Pretend I did it correctly. 4 times 2, 4 times 2. And expanding this a little bit further, we have 2 times 2 times 2. All right, so I think I have that. 1, 2, 3, 4, 5, 6, 7 of them. All right. So 128, 2 to the power of 7. If you wanted to double check and make sure that was correct, just take these, pop them in your calculator, and if you've done it correctly, they should give you 128. Okay, so I'm just going to scroll down a little bit further here instead of continuing up top. So we had the cube root of 128 times x to the power of 4. So this is the cube root of, now you don't have to write all these factors individually. I'm just going to do it in this one case. And don't forget we had x to the power of 4. That one can also be divided up. So those are all of the prime factors, including the variables, for the cube root of 128 times x to the power of 4. Okay, so this is a cube root. We're going to try and take out powers of 3. You can see my video is off center, but it looks like I have it fixed now. All right, so we have 3 copies of a 2 here. So we need one of them out front. We have 3 factors of 2 here. We're going to need to bring one of them out. We have 3 factors of x here. We're going to need to bring one of them out. So a little bit messy, but what do we end up with in front of our radical as the coefficient? 2 times 2 times x. That's 4x times the cube root of what was left over. Well, we had a factor of 2 that did not come out of the radical. We had a factor of x that did not come out of the radical. So this is 2x. Is there a need for a restriction? No, because our index is an odd number. So we do not need a restriction on our value of x, other than perhaps x is a real value. Okay. So next one I had planned. See how I'm doing for time. So it was 5c. So let's move on to that. Sorry, I'm still trying to fix the framing here. I wonder if this will work. Just going to take one moment and wait for my test message to pop up here. Okay. Okay, let's try working with this. So I think 5c. So we had negative 35 times the fourth root of w squared. And we also had 3 times the fourth root of 81w to the power of 10. And we wanted to try and simplify each one of those values. So it showed up on my stream now. I think I should be able to put it there and things should be okay. 81. So let's do our quick factor tree for 81. 9 times 9. Then 3 times 3 times 3 times 3. So 81, 3 to the power of 4. W to the power of 10. I'm just going to do this in perhaps a shorter version this time. I'm not going to write out all 10 W's. I'm just going to group them into groups of 10. 3 times the fourth root. So we have 3 to the power of 4. And 8 to the power of 10. How can I break that up into groups of 4? So I have W to the 4 times W to the 4 times W to the power of 2. So that's all going to multiply to give me W to the power of 10. So what is the end result? 3 to the 4. So we have 4 factors of 3 inside of our radical symbol. So we can take one of those out and factor it. We have 4 copies of W. And we have another 4 here. The W squared that is left over, we don't have 4 factors of it in our radical, so we cannot factor that one out. So what are we left with? So on the outside, 3 times W times W, 9W squared, times the fourth root of W to the power of 2. Now, we have an even root here. So that would imply that we should have W greater than or equal to 0. I think it's okay in this case because we're squaring our value of W. So we're raising it to an even power. Now that I say it, I'm not actually certain. I'm going to put that restriction there for the moment. I'll take a look at it later on. I see that I need it here, I think. Okay. 6b. So we're given 3 different expressions. So we have negative 2 root 3. We have negative 4. We have negative 3 root 2. And we have negative 2 root 7 over 2. And we're being asked to order those from least to greatest. So we're going to have to take these expressions and find a way to compare them without a calculator. So what we can do is we can take all of them and we can change them into entire radicals. Because when they're entire radicals, we just have to look at the radicand and we'll easily be able to compare between them. So let's start with the first one. So negative 2 times the root of 3, which is negative. Now we have this coefficient of 2. If we're changing this to an entire radical, we need 2 copies of it under the radical sign because this is a square root. So that's going to give us negative root of 12. Negative 4, this is the same thing as saying negative 4 times the root of 1. So this is negative root of 4 times 4, which is negative root of 16. Negative 3 root 2, so this is pretty similar to the first one that we did up there. So root of 3 times 2, so this is negative root of 18. And finally, we have negative 2 times the root of 7 over 2. I think I'm going to have to adjust my screen to get this all the way on here. So this is negative 7 over 2 times 2 times 2. And in doing that, 2 divided by 2 is 0. So we're left with negative root of 14. Okay, these are all negative numbers. We're asked to sort them from least to greatest. So that means that whichever one is the largest negative value will be the smallest number. So this one would go first, and then this one would go second, third, and fourth. So looks like we will have negative 3 root 2, negative 4, negative 2 root 7 over 2, and negative 2 root 3. Okay, so those are some problems on simplifying radicals. You'll still need to simplify radicals when you're adding them together. So let's take a look at some problems that involve adding. And specifically, I'm going to look at 9D, I believe, which unfortunately I did not write down the question for. This is on page 279. Okay, so this is 2/3 times the cube root of 81 plus the cube root of 375, all divided by 4, minus 4 times the root of 99, plus 5 times the root of 11. Negative's always kept out of the root symbol. Is there ever a negative symbol in the radicals? I think you mean, so just as a little side thing, I'm presuming that you're talking about something like this, and you can correct me if I'm wrong. So if this sort of thing is possible, so perhaps something like this, and if that is the case, it depends on the index. So if this index is odd, it's perfectly fine to take the cube root or the fifth root or the seventh root of a negative value. You will get a negative answer. But if this index is even, we aren't able to take the square root or the fourth root or the sixth root of a negative value. This will not give us any real solutions, but it is okay if the index is odd. If I look at this example that I have here, this actually, I believe, works out to negative 2x. And we can check that that is the case. Yep, you're welcome. I'm just going to work this through in a little more, because negative 2x times negative 2x times negative 2x. So negative 2 times negative 2 times negative 2 is negative 8. X times x is x cubed. And you can see that this, hopefully they're both on the screen at the same time, but this negative 8x cubed matches what was under the radical symbol. So that matches what was in the radicand there. So it's okay to take the odd root, like third root or fifth root of a negative value, but not the even root. Okay, so let's go back to the problem that I had up here. So 9d. I don't know that I had that all on my screen before, so I'm just going to move it up here. And let's continue on. So we have 4 different expressions. And we want to simplify this as much as we possibly can. So we're going to have to look at each one of these radicands and see if we can simplify them. So what we're going to want to do is find 4 different factor trees. Probably 3, because if I just look at this last one, root of 11, 11 is a prime number. We can tell that that's not going to simplify. But 81, 375, and 99, those may simplify. So we're going to want to do prime factorizations for each one of them. So let's start with the number 81. So 81 is the same thing as 9 times 9. And that gives us 3 times 3 times 3 times 3. 375. So I can see that this is divisible by 5. And I can also kind of see that I think it's divisible by 25. So how many 25s? 4, 8, 12, 15, I believe. So I hope I have that right. Oh, according to my past work, I do. So 5 times 5. And 5 times 3. And finally, 99. We have 9 times 11. The 9 breaks down into 3 times 3. Okay, so there's our prime factorization for each one of those. And again, I'm not going to do 11. 11 is a prime number, so the prime factorization would just be 11. Okay, so let's scroll this up a little bit. And I'm going to start writing the original expression, but I'm going to take those radicands and expand them by using the prime factorization that I just did. So we have 2/3 times the cube root of 3 times 3 times 3 times 3. Can already tell I wish I gave myself a little more room here. I won't make that mistake this time. Times the cube root of 5 times 5 times 5 times 3, all divided by 4. Just looking for where they're showing up on my screen. So let's put this up here. I think that should be okay. Minus 4 times the root of 3 times 3 times 11. And what was the last one? 5. So plus 5 times the root of 11. Okay. Starting with the first term. This is a cube root, so I want to see if any factor occurs inside the cube root 3 times, and it does. So 3, 3, 3. So we're going to move one of these out in front of the cube root. And I can see that this 3 is going to simplify with the 3 in the denominator. So for that term, I'm going to end up with 2 times the cube root of 3. Okay, next one. So we have the cube root. So again, this is a cube root. We're looking for any factor that shows up under our radical symbol 3 times. So 1, 2, 3. So there's 5. So 5 over 4 times the cube root of 3, since one of the 3's did not factor out. For the third expression, move this over a little bit. So 3 times 3 times 11. This is now a square root. So for a square root, I want 2 factors. So 3, 3. So that's going to give me minus 12 times the root of 11. And for the last one, so we just have looks like it's just plus 5 root 11. Okay. Now we want to combine any of these expressions that have the same radicand and index value. So looking through this, I see that the cube root of 3 shows up twice. So that can be combined. And to combine them, I'm going to want to add the index values. So 2 plus 5 over 4. So 2 is the same thing as 8 over 4. 8 plus 5 is 13. So that'll give me 13 over 4 times the cube root of 3. So I'm taking these two and combining them into 13 over 4 times the cube root of 3. Looking over to the final two terms, they both have the root of 11. So I can combine them by adding or subtracting those index values. In this case, negative 12 plus 5 is going to give me a negative 7, I believe. So this is negative 7 times the root of 11. So that would be our fully simplified expression. That was 9D. Okay. I have 2 more planned here, and then I'll ask for any additional questions that you might have. The next one is 10C, and that is on page 279. So page 279, numbers 10C. So simplify each expression. So this is negative 4 times the cube root of 625r plus the cube root of 40r to the power of 4. So before I go any further, part of this problem asks us to identify any restrictions on the values for the variables. Well, note that we have even index values. So it doesn't matter whether r is going to be positive or r is going to be negative. Both values will be okay. We just need r as an element of the real number system if that is required. If these index values were even, however, so if this was a fourth root or a square root, we would have to specify that r must be greater than 0, but it does not have to be in this case. Okay, getting ahead of myself a little bit. Let's start doing the prime factorization here. So 625, I believe, is 25 times. There we go. I believe that's 25 times 25. And that ends up with 5 times 5 times 5 times 5. So this is 5 to the power of 4. Believe it or not, that is a 5. I'm having a hard time believing it. All right. For 40, this is 4 times 10. So 4 is 2 times 2. 10 is 2 times 5. So there are our prime factorizations of 625 and 40. Don't know why I didn't write those values at the top of there either. Okay, let's use those prime factorizations to simplify this expression a little bit. I think I should be able to see it here. So -4 times the cube root of 5 times 5 times 5 times 5 times r plus the cube root of 40, which is 2 times 2 times 2 times 5. And then we also had r to the power of 4, and that's r cubed times r. Or you could write the r out 4 times. It's fine either way. So we want groups of 3, since we're dealing with cube roots. So what factors appear under the cube root symbol 3 times? Well, we've got 3 5s for this first one, so we can take one of those out. We have 3 2s when it comes to the second term. And we also have 3 r's. We have r times r times r. So one of those r's can come out as well. So for our first term, we have a -5 times 4, so that's -20, times the cube root of 5r. For our second term, it looks like I factored out a 2, and I also factored out an r. I don't think there was anything else originally there. There was not. So this is 2r times the cube root of 5r. Well, wouldn't you know it, we have 2 radicals that have the exact same radicand and the exact same index. That tells us that we can add or subtract the values which are in front of those radicals. I'm going to write this portion slightly different than it is in the answer key, because it just makes a little more sense to me to take that to take that cube root of 5r and have that be the expression that's factored out. I think they do it the other way around in the text. So we're factoring this out, and when we do it, what is left over? It's the things that I underlined in red. And I'm just going to switch the order of them here. 2r minus 20. I could have left that as -20 plus 2r, but typically we put the variable first. And looking at this again, I can see that there is a factor of 2. So if I factor that 2 out, what I'm left with is r minus 10. And that is times the cube root of 5r. So that would be our fully factored and simplified expression. We're going to move on to number 17 next, and that is on page 280. I'm just looking at my screen. I have to play head games with myself, thinking about where I have to write it on the tablet for it to show up where it is. I haven't had this issue in previous streams. I don't know why it's happened this time. I think all these values are positive, actually, so maybe it's better to do it this way. Okay, so we are told in problem 17 that an ant travels in a straight line across the Cartesian plane from 3, 4. And I'm not going to measure this perfectly to scale. I just want a rough approximation. So from 3, 4 to 6, 10, I believe. So I think I said I'm not doing it to scale, but maybe I should do a slightly better job than that. 6, 10. And then it travels from 6, 10 to 10, 18. Something like this. we are asked, what is the total difference? What is the total distance that the ant has traveled? So I'm just going to call this D1, and I'm going to call the second distance D2. What is the total distance that the ant travels from beginning to end? So we don't want the shortest distance, we want the physical distance that was traveled. Now, perhaps you recall the distance formula, which is this x2 minus x1 squared plus y2 minus y1 squared. And perhaps you recalled what that distance formula was and were able to apply it to this problem to find those distances. But perhaps you didn't remember what the distance formula was, or perhaps you didn't notice that it's something that could apply here. Distance formula is one way to solve it. I'm going to do it without the distance formula, but I'm just putting that there as one tool that you could use to find the solution to this problem. But I would just like to perhaps take a little more logical approach and build our distance formula that we can use to solve this. What is that red distance? Well, it has a horizontal component. It has a vertical component. And you can see that I can form a right-angled triangle here. What is this point? Well, it's got an x coordinate of 6. It has a y coordinate of 4. I feel that you could probably tell just by observation, once we have that coordinate drawn in, what is this horizontal distance along the bottom? It's a distance of 3 because this whole thing shifted over 3. What is that vertical distance, the one that went from 6,4 to 6,10? That's a distance of 6. So if I want to find out what D1 is, what I can just do is apply the Pythagorean theorem here, and it will be that red hypotenuse of the triangle that I've drawn. I'm going to draw the second triangle as well for D2, and then I'm going to solve both of those below. I'm going to scroll the graphic off once I do it, but you can see that I can sculpt the same triangle here. And it looks like this coordinate would be at 10, 10. And I can see that we would go over 4 and up 8. So yes, I've done an excellent job of drawing this one to scale, I can see. And I can similarly use a Pythagorean theorem to find out what D2 is equal to. So even without access to our distance formula, we can essentially build the distance formula just by drawing in those triangles. This is also the way that you probably were taught it back in perhaps junior high when you were first exposed to these sorts of distance problems. Okay, so let's start with D1. And I'm just going to look back at my triangle here. So I had a right angled triangle and the two side lengths were 6 and 3. So I have D1 squared equals 6 squared plus 3 squared. So D1 squared will be 36 plus 9, which is 45. I can take the square root, both sides. So that tells me that D1 is equal to the root of 45. Does the root of 45 simplify any further? Well, we could build a factor tree to see whether 45 would simplify further. That factor tree would have 5 times 9 as two possible factors. And the 9 could be broken down into 3 times 3. So I hope you'll permit me this shortcut. But if I were to do a factor tree for 45, I would get 5 times 3 times 3 as the factors. Well, we can see that there are a pair of 3's under the square root, so that can be factored out. So our D1 is the cube root of 5. Oh my goodness, is 3 times the square root of 5. I can't help it, there's a 3 in front of the radical. I just want to call it a cube root. d2 squared. Looking back at the triangle that I built up here, looks like it has side lengths of 4 and 8. So d2 squared would be equal to 4 squared plus 8 squared. Four squared is 16. 8 squared is 64. So this ends up being 80. So d2 squared is 80. And we want to find out what the square root of this is. I think I will, even though I worked this out earlier, I think I will just do the factor tree for this one very quickly over here. So 80, oh, red would be a bad idea. Let's go with the best color instead. So 80 is 8 times 10. And those can be broken down into 4 times 2 and 2 times 5. So we get 2 times 2 times 2 times 2 times 5 as our prime factorization of the number 80. So using that, let me continue with d2 equals the root of, give myself room, here we go, 2 times 2 times 2 times 2 times 5. It's a square root. We're looking for pairs of factors under the radical symbol. We have a pair of 2's here. We have a pair of 2's here. The 5 does not have a value to pair up with, so this will just be 4 times the root of 5. Our earlier answer, I think, was 3 root of 5. Yep, okay. So d2 is equal to 3 root of 5 plus 4 root of 5. Same radicand, same index, add the coefficients, 3 plus 4. This gives us 7 root of 5. Okay, that was the last problem that I had planned on going over. There were some initial problems that were assigned on multiplication. Looking across the classroom sites, I'm not certain that the multiplication video has been posted yet. So I'm just going to say, before you try those problems, you can check on my page here, and it's 3.2.1 multiplying radicals. I'll just ask that you go and take a look at that video, watch it through, work out the problems alongside it, and then go back and attempt the problems that were assigned in this lesson. You can email me if you have any difficulty with it, but just to give you kind of like a little bit of more background and more practice problems on it first. My live stream next week will be about multiplying and dividing radicals, and we'll also talk about the conjugate. All of those videos are on the classroom site. You don't have to look at them now. They'll be assigned to you on Friday and Monday, so I would guess that the live stream will likely be on Tuesday of next week.